A queue is another node-based data structure which is used to be able to access data in a form that resembles sort of like a typical queue that you might stand in a grocery store, for instance, or really any sort of store. So the idea is that the first thing that enters the queue is also going to be the first thing that leaves the queue. So the first person to enter the line is the first person that leaves the line, and as we add more people into the queue, they're added to the end of the queue and they're serviced in order that they appear. So the main applications of queues are sort of twofold. It's used in a lot of different simulation type aspects. So for instance, like the grocery store example that I gave you, if we want to simulate a grocery store lineup, we could use a queue data structure to simulate that lineup very easily. As well as that, it can be used in things like process management for operating systems. A lot of operating systems will use queues to be able to determine what process comes next, determining based on the order of the processes that are arriving inside of the queue. So to give you a little bit of an idea of what queues are really about, they're another node-based data structure. And these node-based data structures are going to involve nodes that have values and pointers to their next values, right? Whereas with a stack, we had a top, and we just kept track of the top and everything that followed behind it. With a queue, we actually keep track of a few different aspects. So we keep track of what's currently at the front of the queue. And typically, we're also going to keep track of what is at the rear of the queue. And what we do is we continually track the front and the rear, and when we want to insert new values, we update the rear to point to a new value and then update the rear pointer to point to a different value in the queue. And when we remove values, we remove from the front of the queue and update the pointer to point to a new front value. So the idea is very simple. You can think of this almost as the opposite of a stack. With a stack, we always insert it to the front and remove from the front. With a queue, we insert to the end and remove from the front. It's typically referred to as a FIFO data structure or first in, first out data structure, rather than a stack, which is referred to as a LIFO or last in, first out data structure. So keeping this in mind, let's take a look at how we can program something like this in Python. So we already have our node from before, and what we're going to do is we're going to create our queue data structure. So we'll go new Python file, and we'll call this one queue. And we'll start off by importing our node. So we'll say from node, import node, and our class is going to be called queue. So first off, we're going to start off with our initializer. So we'll define our init function. And with our init function, we're going to set up a front, which is going to be equal to none, and a rear that's going to be equal to none. And then a lot of the time we want to keep track of the size of the queue as well, just to make things a little bit easier to reference like how large the queue currently is. So we'll set up the size as well. So the main operations that we're going to have are insert and remove. Sometimes you'll see these written as on queue and dequeue. Either or is fine. You can really name them whatever you like. For insert, it's on queue. For remove, it's dequeue. So if you see those two method names, they're just different naming conventions. It doesn't really matter which naming convention you use, as long as you're consistent with yourself, right? So I'm going to call mine insert. So with insert, it's going to take in a value. And what's going to happen is we're going to say value equals, and we're going to create a new node. Well, I'll call this something different. I'll say in value equals node, and the node is going to take in the value that was provided to it. And then for now, we'll give it nothing as its pointer. And we may or may not need to update that. Actually, yeah, typically we won't need to update that. And the reason being is because we're always going to insert to the end of the queue. The thing at the end of the queue isn't going to point to anything, right? So the pointer is always going to be none. So we set it up to have the value that's inserted to us as well as a pointer to nothing. And then we're going to check to see if the size is equal to 0. If we currently have an empty queue, so it should be self.size is equal to 0. If we currently have an empty queue, the operation to actually insert the values is going to be pretty straightforward. What we're going to do is we're going to update the front to point to the new node that we created. And we're also going to update the rear to point to the new node that we created. If there's only one value inside of the list, the front and the rear are just going to point to the same thing, right? The front is also the end of the list, which is the only value that's inside of the list. And then from here, when we insert values, we're just going to update the rear as well as the pointer from the rear, right? So on the else for this, if we have any values inside of our queue, what we're going to do is we're going to say, well, now what's going to happen is the rear is going to point. So we're going to say set next equal to in value. So the thing that's currently at the end of the list is going to point to the new value that we're inserting. And then we need to update it to say the new thing at the end of the list is the value that we just inserted, which is going to be self.rear equals in value. So what we've done here is, so if we have a new list with nothing inside of it, we just simply set the front and the end to the same value since there's only one thing inside of the list. Otherwise, we're going to set the end value to be pointing to our new value. So like if we were to draw this out in our diagram here that we had, right? We would be able to see, so for instance, if we're inserting into this list the value 4, right? What would happen is we would first update the rear to point to the value 4, and then we would update the rear pointer to point to this new end value. That's the steps that we're taking in order to get to this. We're just simply updating the end to point to the new value and then saying the new end is that new value that we just inserted. And then finally, of course, we need to increment the size every single time to be one bigger than what we started with. So this is our insert operation. Our remove operation is actually going to look really familiar. It's basically the same remove operation as the stack, right? What we do is we say the value is equal to what's currently at the front. So we do self.front.getValue. And then what we do is we say self.front.setNext. So we're going to set the next, we're going to set the front equal to the front's next value, right? And then we can just return the value that we got. So what we're doing here is we're getting the value that's at the front of the queue, and then we're updating the front to be equal to, this should be get next, right? We're updating the front to be the next value in the list of values. So it essentially gets the value that's at the front of the queue and then moves the front forward one link inside of our queue, right? So this would be the simple idea behind the remove. Now, of course, we want to make sure that there are actually values available to remove before we do this. So it would be ideal to say if self.size is greater than 0, then we can do all of this. And then otherwise, we're just going to return, right? We could just return nothing, or we could print an error, or we could do whatever we want on that else, but we just want to make sure that there's something actually available for us to remove before we attempt to remove something from the list. So the final thing that we also want to do here is we want to decrement the size whenever we remove something from the list. So we want to minus equals 1 from the size, right? Because every single time we remove something, we want to continually update that size property to make sure that we aren't, keeping the size constant even though we removed something from the queue itself, right? So these are our core insert and remove functions. If we want to test this out, we could take a look at our main here, and you'll see that I've imported the queue and I've created a new one, and then I insert some values into it, and then I also remove them to test to see that everything is working. So you see when we run this, we get 1, 2, 3 as our output. Because you can see that we inserted those in that order, right? We inserted 1, and then 2 would be behind it, and then 3 would be behind 2. So when we remove, it removes the first value each time, value 1, value 2, and value 3. So those are the typical sort of node or queue operations that we would implement. There are a few other operations that might be of value to us, so we'll go ahead and implement a few other pieces here. The first thing that we're going to implement is the peek operation. So similar to a stack, the peek will tell us what is currently at the front of the queue, meaning it's just going to return self.front.getValue. So this would be a way of being able to tell what's at the front of the queue before we actually remove or do anything like that. So that's one operation that could be helpful for us. Another one that's typically done is getSize. And this is going to return self.size. Now, one thing that I want to mention here that may be of interest is that rather than using getSize, you can also do the following function, __len. What this will do is rather than having to type in like q.getSize, I'll show you here. So rather than typing in something like q.getSize, what you can do instead is you can use the built-in len of q. And what will happen is this will trigger this length function. We refer to this as overriding the function. So we're changing the functionality of that len function specifically for our object. And we're telling Python, when you get that len like function, you should use this logic that we written into this method. So that's something I want to sort of bring up that I haven't really talked about yet. You can use this sort of property here to overload the function. So you could have used this for, if we were doing like length inside of the stack as well, you could have used that. But this is a sort of interesting way to do it as well. So just to show you this, let's just go ahead and print this here just to show what it would look like. So you can see here we get 3 because the length of the queue is currently 3 values, right? So you can see that this works the exact same as just like returning self.size. Just since we use this __len, it overrides the length function in Python, which allows us to use the len rather than having to like get size or something like that. So I just wanted to show this because oftentimes a lot of people will do this. So if you ever see that function, just know that it's equivalent to doing that len, right? So then the last thing that we can sort of implement here that's common is an isEmpty function. And there's a few different ways that you can do this. My preferred way would be to do like self.size equals 0. You could also do like self.front equals none. But I like self.size equals 0. It's just a bit more reliable and a bit easier in terms of the logic. So overall, these are the main functions that you would typically implement inside of a queue. So these methods are going to allow you to do most basic queue operations and be able to utilize queue data structures inside of your programs. There are, of course, other methods that you can write for the queue, but these are the main basic ones that would be helpful towards most programs.